Good morning, good afternoon, and good evening, everyone. So today we're going to be continuing our calculus series, and we're going to be talking about tangent planes and linear approximations. And apparently, this is one of the most important ideas, especially in single variable calculus, right? Um, and so we zoom in toward a particular point on the graph of a differential function, a differentiable function. Okay, so the idea is that the graph becomes indistinguishable from its tangent line, and we can approximate the function by a linear function, right? And here we develop similar ideas in three dimensions as we zoom in toward a point on a surface that is the graph of a differentiable function of two variables. And so the surface looks more and more like a plane, so it's tangent plane. And we can approximate the function by a linear function of two variables. And we also extend this idea of a differential of um, this idea of a differential to functions of two or more variables, right? So what in the world did I just say? In calculus one, let me just. How do we find a derivative? Let me. So in calculus one, the way we find a derivative in functions in 2D functions, say we're given an xy plane, and let's say we have a graph or we have a curve. We call this a plane curve because it's a curve on the plane, right? And let's say, I don't know, this is y equals f of x, right? The typical, let's say it's a function where we plug in some x, we plug in some x, we get a corresponding y. So this is the point xy, right? So that's the basics. Um, how do we take its derivative at a particular point, right? Well, when we're taking, crap, I keep on deleting it. When we're taking a derivative, right, we specify some point. I don't know, let's specify that point. So at that point, um, we have a line, right? So we have some line that tells us how or what is the rate of change or how fast are we going, right? If we want to contextualize this problem. And we call this the derivative at this point. We call this, I don't know, let's say this is okay, I'm not even gonna do A. Let me do some point x sub one, right? And so what is this? The output's gonna be, well, f of x sub one. And so how do we take its derivative? Well, we get the function and then we take its derivative at that point. And there we can determine how fast or what's the rate of change at that point. And we also call this the derivative. We also call this the tangent line at that point, right? But in calculus 3, where we're talking about 3Ds, so let me reiterate. This is what we call a tangent line. And to be specific, it's the tangent line at the point x1, f of x1, right? So it's that. We can take the derivative, do some analysis and whatnot. But moving on to Calc 3, well, here now we talk about not tangent lines, but tangent planes. So here we're given a 3D space. Oh, so we have my XY plane, as well as my, well, my XY axis, as well as my Z axis. And so we call this a 3D space. And from here, well, we can see, oh, okay, let me do a quadric surface. Let me do a curve. It's not even a curve, actually. If you want to draw something in space, it has to be a surface. It could be a curve, but, well, it has to be some surface. Let's say that's the surface. And, well, how do we find, let's say there's a point on this surface, right? And then from there, oh, okay, we can find derivatives at that point. We actually find two, right? And we did talk about this. We can see there's a derivative there. So that's one tangent line. Another one could be, I don't know, some tangent line here. Some tangent line here. And those are two. And how do we find each of those two tangent lines? Well, we don't take derivatives, just like this one. We take partials, partial derivatives. Um, so yeah. And well, as we continue, or based on these tangent lines, right? Based on these tangent lines, we actually get this thing called a tangent plane. So this is what we're talking about in today's video. Because last time we talked about partial derivatives, now we're going to relate it. And now we're talking about a tangent plane, right? And so let me actually erase this picture because this is a very bad picture. I'm going to use a picture used in my textbook, so that's easier. So, okay, I can't see my head anymore. Okay, so the picture that my textbook used in this case is sort of like this. Okay, let me take a screenshot and paste. Voila. And here we can see that, oh, we have some labels here. Well, let me just tell you what those are. T sub 1 and T sub 2, those are the tangent lines. The red lines, those are the tangent lines, right? And you get these by taking partial derivatives at this specific point P, right? It's talking about this point. Let me use a different color. Oh, that's even worse. I'll just use black. There we go. So it's at that point. We have these two tangent lines. We get their partials. And then from there, we get a tangent plane out of it, right? And this tangent plane contains both of these lines. It contains T1, that tangent line, and T2, right? C1 and C2 are the curves of intersection. And we did talk about this in our previous video in my calc series on partials. So okay, let's actually dive deep into what this is mathematically. What are tangent planes to be exact? So tangent planes in the mathematical sense. Let me So tangent planes, suppose we have our surface, right? Let's call it S. So this blue thing, right? That's our surface. We'll call that S. We call that a quadric surface. Um, and let's say this has some equation. It has some equation. I mean, everything in math has an equation, right? And yeah, we did talk about this. And let's say it's an explicit function of z. So we have z is some function. We put in f and x and y, and we get an output z. So this is an explicit function of z of this quadric surface S. And we're going to say, so that this thing works, is that f is going to be continuous. So it's going to be continuous, or not is. It has, my bad. It has continuous, we're going to say first partial derivatives, right? So what does that mean? Well, in calculus 1, in order to take a derivative, or in order for a function to be differentiable, well, it has to be, well, one of the perks, I guess, or one of the conditions that it has to fulfill is its continuity. It has to be continuous. So no holes, no gaps, no nothing. Just pure, smooth, continuous, no sharp points. And here in 3D, it's the same thing. Well, in order to take partial derivatives, well, one of the conditions, I guess, is for f, our function f. In this case, our um, equation f has to be continuous. So here we're just describing the general idea. And let's say we have Rp. So let's let P be our initial point. So this P is talking about this P. Need three variables. I don't know. I'm just gonna call them super general. X naught, Y naught, Z naught. And this is a point literally on S. It's on S. And there we go. That's the initial background. So here I just described this whole picture, using what we call English. Using yeah, but we just described that picture. Okay, so after describing that picture, well, previously on our lecture on partial derivatives, we were able to talk about intersecting curves. And so we let C1 and C2. I'm talking about the C1 and C2. The one with the dashed lines. How in the world did we get those again? Well, we had planes that intersect this quadric surface S. And so what was that? Let me continue this. So they're intersecting curves. And how do we get those curves? They're obtained by intersecting vertical planes. So that's how they were obtained, right? And these vertical planes are, well, some x value and some y value. So where y is y naught and where x is x naught. So that's how we were able to obtain these two, right? We were able to find a plane that that's specifically at y naught and x naught. So let me quickly draw this. So at y naught, it's uh let me so this is the point, right? It has some x naught, y naught, z naught. So x, let me just go down. So if I go down, that's the y, that's the x. X naught, y naught. Now, what were the planes? For y equals y naught, well, this is the plane. There we go. Don't expect my drawing to be super good. It's that plane, right? Actually, this looks ugly. My bad. I didn't mean it like that. Why not? So it's this plane there, right here. There we go, much better. And then we just, yeah, go from there, right? So it kind of intersects here, where, right? If we intersect this y equals y naught plane, God, my drawing is not. Yeah, that's the idea though. If we sort of make a vertical plane and we try to get the intersection of both, well, we should be able to get that. And then for our x naught, God, my drawing. For our x naught, it would probably look, let me do a different color. Look something like this. I'm just drawing from my x naught. I'm just drawing literally that vertical plane. And well, it's going to somehow intersect here. So when I intersect that S surface and then that vertical, and then it's going to intersect there. I wish I had a way to do this like really nicely. But yeah, that's the idea. Okay. So those are the vertical planes. And what else? Okay, let me just complete. So we intersect these vertical planes with our surface S, right? And then the point P lies on both C1 and C2. So they lie both, this point P lies on both these intersecting curves C1 and C2. I'm not gonna put that anymore. T1 and T2 are the tangent lines to the curves C1, C2 at that point P. And then the tangent plane to the surface S at that particular point P is defined to be the plane that contains both tangent lines T1 and T2. So let me just put a description of that. We're saying uh, P lies on both C1 and C2. We could even say it lies on both our tangent lines. Um, anyway, we don't have to. And we're saying T1 and T2 are tangent lines. Specifically, to our intersecting curves, C1 and C2, right? And then from there, well, what now? Now we talk about the tangent plane. And so the tangent plane is basically the, let me, it's the plane to the surface, so our surface S, at a particular point. So let's say at point P. And we're saying, okay, it's defined to be the plane that contains both. And contains both our tangent lines. I don't need to do that. T1 and T2. So that's the idea. This tangent plane contains both T1 and T2, right? And so I'm saying these red lines, right? Well, they're literally on the tangent plane at point P in surface on surface S, right? God, if there's a visual. Okay. And we will see in future sections. So this is what, section 14.4? Yeah, 14.4. We're going to see 14.6 that if C is any other curve on the surface S and passes through P, then its tangent line. So the tangent line at that curve C at particular point P also lies in the tangent plane. So really, you can think of the tangent plane to our surface S at that particular point P as consisting of all possible tangent lines at P, right? So we can say that, okay, let me draw something just to illustrate what in the world I'm trying to say. Let's say we have our 3D space, or z, x, y, and we have a quadric surface. Let's do that again. Let's do the looking like saddle thing. And let's say that's our surface. And we have point P that lies on that surface S. Let's call this S. I'll call this P. And then from there, we have tangent lines, right? We take partial derivatives. But what we don't realize is that we actually can take a lot of that tangent lines. So why not just draw a tangent plane, and this tangent plane contains all of those lines, those infinite number of lines that are tangent to this point P at surface S, right? And so here's what we're looking for. This tangent plane at point P on surface S. That's the idea, right? We're just looking at that tangent plane. And the idea is if we take a lot or infinite amount of tangent lines at a particular point, then why not just make a tangent plane out of it that contains all of those tangent lines, right? So that's the idea, right? Okay. And so, yeah, what else? The tangent plane at that point P is the plane that most closely approximates the surface S near the point P. And so we, again, can use that to approximate, well, surface S and do some more analysis with that surface. Um, okay. And we know from a previous topic, the equation of a plane passing through any point, right? So let's do a brief recall. So previously we talked about equations of planes, right? This was week 2. If you guys want to check it out, it's equations of planes 12.5. Yeah. Every time I do my videos, I always put like what number we're at. So this is 12.5. And here we see that, where was it? In order to get the equation of a plane, and we're saying that point is on the plane, we have a formula for it. And it's loading. Okay, screw it. There we go. Got it. So the scalar equation of a plane through the point, and it has this normal vector n, is this, right? We have our initial point x naught to z naught, x, y, and z, given some point, and then, well, we have our normal vector n with components a, b, and c. And so that's the idea that we're going for. Let me go back. Oh, can I? It's not loading for some reason. That's funny. Why is it not loading? I can write stuff. Oh, there we go. Nice. Okay, let me week 5. Okay, so recall any plane, whether that's tangent or just a regular piece of plane, any plane that passes through some point. I don't know what point that is. Has an equation. I'll do capital because the textbook says capital. There might be some meaning to it, but I just want to assume that's a normal vector. That could be any numbers anyway. And that's equal to 0. All right, so the idea was, right, if we want to find the equation of a particular plane, well, what do we need? We need some point on that plane. So that's the initial point, x naught, y naught, z naught. And we need some normal vector. How do we know it's normal? Well, it's perpendicular. And this vector has to have a, b, c components. And then from there, we can find the equation of that plane. Right? Okay, cool. Now what? So what happens if we know this? Well, we can divide this equation by c, right? So let's do that actually. Let me do that. So let me divide this equation by c. So we get a of this divided by c. This one is just, okay. So this one is just z minus z. And then this one's just 0. And then from there, well, what's going to happen? Let me switch it around. I'm going to completely isolate this term here. So this is going to be z minus z naught negative minus this. Right? Then after this, we're going to let a be negative a over c. And then b. 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 Okay, I'm gonna stop doing that. We're going to let b equal negative b, capital B over c. And so that's going to be, that's so many b's. A plus b, right? That's what we get. And let's say this, we're gonna call this equation 1. At least that's what my textbook is doing. And then from there, if equation 1 represents the tangent line at B, so let's say this is the tangent line at B, then its intersection with the plane y equals y naught must be the tangent line T1, right? And so if we set y equals to y naught, then we just completely take out my second term in the right-hand side. Okay, let me just try to. If this represents equation, or no, not equation, tangent line. Oh, what am I saying? Tangent plane, my bad. Let's say this is the tangent plane at P, right? Because this is a plane equation. And we're given that initial point x naught, y naught, z naught. And we have this tangent plane at that particular point P. Well, its intersection, because we did talk about vertical planes, right? So its intersection at this vertical plane y equals y naught must be a tangent line. And we did do that in our previous video. We're going to call that T1. And so from there, well, if we set y equal to y naught, then we just get z minus z naught is a x minus x naught. Okay, my handwriting is getting messy. Where my y is y naught. Because if this was y naught, let me actually do the computation. If this is y naught, well, then that's just 0. 0 times b is 0. So we have this plus 0. So basically, we're left with this. And what does that tell us? Well, this is actually an equation in point-slope form. So it is a line. If we think about it, this is a line. And it has slope A, right? So here we're going to say, we actually recognize this form. And we recognize this as point-slope form of a line. So point-slope form is a pre-calculus thing. And the slope is A. And from our previous section 14.3 on partial derivatives, we know that the slope of the tangent T1 is f sub x, x naught, y naught. Right? And so here's the idea. So this is slope A. What else? We know that the slope of our tangent. So when we're looking at the slope of our tangent line Q1 is f sub x, right? We did talk about this. X naught, y naught. And so we can just replace A. A is f sub x, x naught, y naught, right? As easy as that. And so that means our other tangent line, when we do a partial on y, this is our other one, it's just f sub y. That's the other partial. partial derivative, right? And so now we have an equation of a tangent plane. Voila. See, what's good about math is you learn something so basic and then you build up complexities around it. And then you start to appreciate the beauty of how like these things come together. Okay, let me do a scenario. Let's say f has continuous. That's our assumption, right? It has continuous partials. And from there, an equation of the tangent plane. And let's say this tangent plane, or not tangent plane, tangent plane to the point on the surface. Let's say the surface has this explicit z of f x y, right? And yeah, so it's tangent to a particular point. And let's say this point is P. So we have x naught, y naught, z naught. And there's our formula. Z minus z naught is equal to our partial x naught, y naught, x minus x naught. We're going to add my b. Or instead of b, we call it f sub y. And I think this is y minus y naught. And that should be it. This is the most important thing that we have to consider, right? This idea of tangent plane equations. Right? Okay. I hope that made sense. We're just deriving from what we previously know. Okay, let's look at an example and try this out. Watch how we're going to find the equation of the tangent plane. Find the tangent plane. I jinxed it. Find the tangent plane. Specifically to the surface. And this surface is an elliptic paraboloid. And so what do we know about ellipses? Well, they're elongated circles, right? What do we know about parabolas? Well, they're a second order polynomial, second degree polynomial, not second order. And so we should have an equation like this. Well, it's actually given 2x squared plus y squared. There's actually a trick to naming these things. If you cancel out each variable, you can get their traces. Describe if it's either three things: an ellipse, a parabola, or a hyperboloid. So we can do that, but I'm not gonna do that now. That was in a very previous video. If you guys want to check it out, it's actually where was it? Quadric surfaces. 13.3? No, it's 12 actually. It's 12.6, which I talked about cylinders and other quadric surfaces. So if you guys want to check that out, feel free to do so. Okay, so we have this elliptic paraboloid, and we want to find the tangent plane at that surface, specifically at the point 1, 1, 3. Right? Well, what do we need? Well, we already have this elliptic paraboloid, so we can. Well, yeah, we need to take partial derivatives. Obviously, we have our initial point, so we can use that. Yeah, first we need to translate this elliptic paraboloid into the the equation that we want. Okay, so or actually, let's do the easy ones first. Let me take its partial derivatives, actually. So find partial derivatives. That's our first step, just to make this easy. And so here, well, we have z equals to x squared plus y squared. Let me take its partial derivatives. We're going to say f sub x. Oh, let's do this step by step. So our partial is f of xy, 2x squared plus y squared, right? And so if we want to take our x, or something with respect to x, well, we're going to have to treat y as a constant, and then we treat x as a variable. So this is just 4x. That's it. And then if we get our f sub y, we treat x as a constant. So we get 0. Here we get 2y. That's it. And then if we plug in what we know, so we plug in the 2 points, our x and y, so 1, 1. Here we get 4 times 1, we get 4. And then for our y, well, we get 2. So easy stuff, right? This is, I think, one of the easiest stuff, taking partial derivatives. And we get the slopes at these particular points. And then from there, we're done. We're actually done. So we just have to fill in or use our formula. Let's just use tangent plane formula, right? We have our z minus z naught. Z naught is 3. F sub x of x naught, y naught, that's 4. And then I think it was x minus 1. Yeah, x minus x naught, so x minus 1 plus f sub y. So it's 2, y minus 1. And then that's it. We're done. We just plugged it in. And we can simplify. Okay. And so let me just show a picture of what that actually looks like underneath the hood. Here's the picture. I want this to be as interactive as we can, but I'm not really good at graphing stuff. Or drawing. Let me just do pictures. Okay, so here we can see from the first figure, it's an elliptic paraboloid, right? I'm talking about this thing here, this squiggly thing, right? That was an elliptic paraboloid. And what its tangent plane is at 1, 1, 3. So it's at, I'm guessing, this point here. That's 1, 1, 3. Right? I don't know. 1, that's 1. For my y, that's 1. For my z, that's, okay, I can't really see it. Also, there's in intervals of 20s. So that's z. From down here, that's z. Anyway, something like that. So it's at 1, 1, 3. That's the point of tangency. And what else? In the second picture, right? And as well as the third picture, as we zoom in toward that point, so here we're zooming in, well, the graph becomes flatter, right? And this is actually the same idea from Calculus 1. If we zoom in, a real value function in Calculus 1, right? So it's just single variables. If we zoom in, we're actually going to see the graph flatten, which means we're getting the tangent at that particular point. And so the idea is that the elliptic paraboloid appears to coincide with its tangent plane as we zoom in. We're going back again to this intuitive definition of what it means to take the derivative. But here we're just doing it in 3D, so that's the difference. Okay. And yeah, we can also do this using contour maps. I'm not gonna, yeah, the textbook did it with contour maps. But we can see basically if we have a contour map of our quadric surface, if we zoom in, the level curves will basically look like parallel lines. So that's what's gonna happen. Okay, let me do more exercises here. I'm going to go to my homework and do some exercises. And we'll see from there. Okay. Let me. Pretty sure I went long on deriving that whole thing. Anyway, 13. Oh no, where was I? 14.4, I think. Yeah, 14.4. Okay, let me do this real quick. Nice and easy. I'm also taking my time here just because I want to really get the idea of tangencies. Okay, let me do some examples for my, oops. So that's 14.3. I want to make a new one. Okay, 14.4. Let me do number one. So of course, we're being asked to find an equation of the tangent line or tangent plane given a surface. So here we're just trying to do that repetition thing where we do it again and again until we figure out the pattern and until we're good with it at specified point. So if we see this, we immediately take partial derivatives, take the formula, done. Right? That's the quickest way to do it. Here's the quadric surface. And then here's the point. 1, 1, 1. Okay, so first thing I want to do is take partial derivatives. Okay. Here's what I'm going to do. Partial. Okay. So here, let me do f sub x first. And then these are two variables, right? 1, 1. We'll do it xy first. Or I'll do x on y not, because that one's easier. Did I do it that way? I think I did it x and y, right? Or I just didn't bother. I just put f sub x. Okay, I'm just gonna put f sub x so that's more simple. Okay, this is gonna be equal to, how do I take the derivative of square root of xy? Here we have to translate the problem. So firstly, I'm gonna put an xy to the power of 1/2. And then I'm gonna separate it because I tend to find this easier. So when we're doing calculus, we want to make sure to get rid of square roots, and we also want to make sure we divide these things. Here we see that, okay, y is a constant, so we leave our y be. We can completely ignore it, right? So let's ignore my y. My x, well, I have 1/2 x here, or x to the 1/2. And if we take the derivative of this thing, right? So here I'm taking derivatives. If we take the derivative of my x to the 1/2, well, I get 1/2 x minus 1/2. And then from there, this is just really automatic. I put it down, I get x 1/2. And then my x 1/2 becomes square root of x. And so automatically when I see this, the derivative of x to the 1/2, I immediately just write this one out. right? And then see here, this is y to the 1/2. I could just leave this as square root of y, which looks nicer. So I'm going to say 1 over 2 square root of x. And then again, this was y 1/2. Well, I can rewrite this as square root of y. Oh, I can put this up here. Square root of y. And then we're done, right? Okay, let me do the same thing. So my f sub, so again, this is just a skill in taking derivatives, right? So let me do the same thing. Okay, let me actually, I'll just copy paste it. I don't care. I'm gonna copy paste up until here, right? Because this is all of the setting up. Or I could actually just completely ignore the other one. But that's fine. Let me just show the complete steps. So I would do the same thing. Oops. Why is my pen not working again? Okay, cool. Very, very nice. Let me go back and do my sharing screen again. Um, yeah, I don't know. I don't know what's wrong with my pen or OneNote. Okay, I hope you guys can see my screen. Good. Okay, so here in this case, we treat x as a constant, and now we do the same thing with y. So actually, what just differed here? What happened is that we just switched the roles, and we're gonna get the same thing, right? So this is gonna be 1 if we take its derivative, 1 over 2 squared y. We just change the variable. And then this is gonna be, if we don't take the derivative, it's square root of x. And then we just multiply these two things, and we get this, right? So we're just switching the roles. Cool. Okay, now that's step 1 down. Now we want to plug in values. So we want to get their f sub x and f sub y at the particular point. So let me just do that. So here I plug in square root of 1, 2 over square root of 1. Well, I just get 1/2, right? Let me do the same thing. My f sub y, well, nothing really changed. I still get 1/2. I get two tangent lines with the same slope, right? Okay, what else? We have our initial, no, we're done. We're done, right? So just to put the formula out, z naught, f sub x, x naught, y naught, right? X minus x naught plus f sub y, y minus y naught. Let's plug in z minus 1, 1/2 of, I think, x minus 1 plus 1/2 of x minus 1. Right? And then that's it. We're done. We can simplify. I'm not going to simplify. Do I need to? Nah, I don't think I need to. I could just make this x plus 1. I could just do that. But I don't. Actually, you know what? Fine, let me do that. That looks super clean. There we go. Now we're done. Z minus 1 is equal to x minus 1. Right? Can I watch it and see? Okay. I'm just gonna check if the answer is correct before I do something really bad. Z. Oh, shoot. I almost messed up. This was supposed to be a Y. Okay. See, that's how I know I was gonna mess up. God, this is why I don't want to simplify. Okay, we're good with this. I'm not gonna do anything anymore. So z minus 1 is 1/2 of x minus 1. We're gonna add 1/2 of y minus 1. And then we're done, right? Got it. Okay, next. We're gonna do the same thing again, but with uh, a different surface and a different point. So number two, the same thing, but just different things too. Different surface and different point. So our surface has z of, oops, forgot my y. Y times ln, or natural log of x. And it has the point 1, 3, and 0. And from there, we're being asked to do the same thing. So again, let's take the derivative. Yeah, here we basically figured out the pattern. Now the only issue is, do we remember our calculus 1 stuff? Can we take the derivative? So let me just do that. F of x, f sub x, I mean. So we take the derivative of this thing. Here we see y is a constant. Y is a constant. But let's make it general, because I know at the next, when I take the derivative of with respect to y, then I have to. So I'm going to make a product rule out of it, right? We did talk about product rule, a derivative technique. Oops. Speaking of product rule, I almost messed it up. There we go. And we'll see from here what we'll get. So here, well, we'll actually just get y prime. This is 0. So this is everything gone, right? Because that's 0. This one, on the other hand, is what? 1/2, 1 over x. I almost said 1/2. It's 1 over x. And there we have it. It's just y over x, right? Let me look at my f sub y. So again, I'm going to do the same thing. Actually, I think I shouldn't have done it because I was just going to do it here anyway. So the derivative of my y here in this case is 1, right? So here I have 1. What is this now? This is a number. So this is 0. So I actually just have ln x. And that's it. Right? Ln, yeah, that's it. Then from there, we plug in what we know. So we have my f sub x at a particular point. 1 and 3, right? We're plugging in 1 and 3 because it's two variables, our x variable and our y variable. This is going to give us 3. 3 over 1, 3. And then for f sub y at 1, 3, we plug in ln of 1, which gives us 0. So here we actually have a horizontal slope at that point. We have a horizontal slope there. Completely horizontal. I'm just double checking. ln of 1 is 0. Right, now let's plug in. So z minus 0, because this is 0, equals my f sub x, so 3, my x minus my 1, or x naught, plus 0. Actually, I don't need to put anything here. Anything multiplied by 0 is nothing, basically. So we're done. We could even do z is equal to 3 times x minus 1. So we could do that. I'm not going to bother. I'm going to write it out, though. Z equals 3x minus 1. 3 times x minus 1. So I could do it like that. And hit submit, see what happens. Got it. Okay. We actually have a couple more with this. So let me just quickly do that. number 3. So we're being asked to do the same thing, actually. So let me quickly do that. I'm just copy and pasting these things. Okay, so now our next item is, looks like we have an exponential here. E to the x minus y. Then we add 6. And then our point is 1, 1, 7. And then now what? What do we do? Take partial derivatives. I think that's the only step, and then plug in. Okay, so f sub x. So we take the derivative of this thing. Oh, I forgot the plus 6 part. This is just 0, let's be honest. So here we have e to the x minus y. See, that's chain rule. Then x minus y derivative. And now this is where it starts to be different, because now we don't know which one is which, right? So let me do this. So y is a constant. That means that's 0. So we're actually just left with x. What's the derivative of x? Well, it's 1. So 1 minus 0 is 1. And then if we put that here, well, we actually just have e to the x minus y. And then that's it. And similarly for f sub y, well, we're going to encounter the same thing. Here our y is 1, our x is 0. So here we have negative e to the x minus y. And from there, we just plug in. So f sub x of my x and y points, so 1 and 1. Well, this is just e to the 1 minus 1, e to the 0, which is just 1, right? Then my f sub y is negative e to the 1 minus 1. And so it's actually negative 1, right? And then from there, well, now we plug in. So z minus my z coordinate, so 7. My f sub x, so that's 1 times x minus 1 and y minus 1. Or not plus, minus, because we have a minus there. And there we have it. Done. So this gives us the equation of the tangent plane at that particular point. We're just practicing on how to use that formula, right? Let me see if we got it. Nice. Okay, we have one more, and then we should be good to go. I'm gonna stop this video and then do next one on linear approximations. So here again, oops, we find the equation of the tangent plane given a surface at a specified point. So let's quickly do that. Z is ln of x minus 3y. And then here we have 10, 3, 0. And then from there, okay, let me take partial derivatives. So here actually, once we're given a point, we should be good. A point and partial derivatives, we should be good. Let's do f sub x. So we, again, take the derivative of this thing. Here we get 1 over what's inside my natural log. And then I do a chain rule here. And from there, it depends. whether my x is my constant or my y is my constant. Here in this case, my y is my constant, so this is just 0. My x is 1, so I just get 1 over x minus 3y. Then that's it for my f sub x. For my f sub y, on the other hand, so let me do that. Now here my x is my constant. I have a negative 3y. So the derivative of that is negative 3. So here I have negative 3. And then now I can take their derivatives at specific points. So here we're looking at 10 and 3 because my x and my y coordinate at my specified point is 10 and 3. And this will give me, well, 1 over 10 minus 3 times 3. And so that's 1 over 1. That's 1. 10 minus 9. 3 times 3 is 9. 10 minus 9 is 1. 1 over 1 is 1. My f sub y, on the other hand, will also give me, okay, let me put the full solution. There we go. Negative 3. 10 minus 3 times 3. Here, this is negative 3 over 1. And so actually, I just get negative 3 here. And then I'm done. So z minus z naught 0. I'm just going to put everything. This is 1 times x minus 10 plus, or well, minus 3. Because my f sub y is minus 3. And here we have y minus 3. And we're done. Okay, that's it for today's video. I hope you guys learned and, well, found something new and interesting to learn about tangent lines. Here you realize it's actually a line, but now instead of just x, we have a y this time. That's the only difference. And after that, well, it's just a once we added that other variable, that's what made it a plane. Now maybe another thing to ask, well, beyond what we're learning and just plugging in formulas, is what if we were to add a certain number of variables, right? So that's another question that we could ask. Let me just quickly finish this, and I'm gonna explain it in a bit. And I hope you guys can answer if you guys watch this video. I'm also curious what you guys think. So just something to think about. Let me submit first before I keep yapping. So, okay, that's good. So when we're dealing with lines, okay, why did I do blue? A line equation is just something of y equals mx plus b, yeah, that type of thing. Y equals, in point slope form, well, it's actually our slope m, our x minus some initial point, x naught, and then our b, which is just y naught, right? And then we just realized from here that m is just the derivative. Let's say that's a function. So our derivative at that point. So that's how we keep on building these types of stuff, right? And then now we look at it from a plane perspective. So from a plane, now we have y, well, we have z. We have z minus z naught. And then f sub x. So here's just something to look into. And then I add my derivative at that point. Here you notice the pattern, right? So this is one thing or two. Yeah, this is a derivative of one variable. is the derivative of two variables. What if it's 3 or 4? How would 4 look like? X, Y, Z, A. Let me just do X sub 1 all the way to X sub 4. Or even general. What if it's just all the way to some terms? X1 all the way to some Xn. What does it look like? Is it a line? Is it a plane? Is it something else completely? Is it a zombie? No, I'm kidding. No, it's not a zombie. What happens? Is it a cylinder? I don't know. What would it be? So those are just some interesting things to look into, I guess. Maybe a research topic. I'm not super sure, but you guys can look that up. And I'm also curious to find out what you guys think. But yeah, that's all for today's video on tangent planes, and I hope you guys enjoyed. Hope you learned a lot, and I'll see you all in the next video.